All right. Hi, everybody. So we're going to be working on worksheet 19 today, and we're not going to be doing much in R other than entering a command here or there. So might be helpful to have R open just to do some of these calculations, make sure they're working, but you won't need more than just using the console to do one command in R here and there. Okay, so yeah, welcome to the final week of stat theory. So first of all, I just want to say thanks everybody here and at watching at home for your responses to the FCQs. It was awesome. We have like 93%, so I think that's everybody but one. I think that might have been a record. So thanks so much for all of your responses. That's really helpful. And secondly, I want to just kind of make sure that the plan for this week and the exam next week is clear. So today we're going to wrap up the material for the semester. The stuff that we talk about today is not on your homework assignment, but it is included on exam 3. So just keep that in mind. So we're going to kind of wrap up the material today. And then the plan for Wednesday is I can talk just generally about the exam, some things to be mindful of. I won't prepare to say too much about the exam, but we can use it as like an office hour type of thing. If you've got some questions as you're getting ready for the exam, certainly feel free to bring them by. But I'm not going to be kind of working through a problem set next time. It'll be more office hours type of environment. So if you do have any questions and you do want me to do something in particular on Wednesday, I'll take requests. So feel free to send me an email and say, hey, could you work on this? If you let me know in advance, it'll probably be a little bit smoother, but I'm happy to do stuff on the fly as well. And then we've got our exam 3 a week from today. So right at this time next Monday at 2 p.m. we'll start the 3rd exam. It's not a final. It is on the material that we covered since exam 2. So that would be chapters 6 and 7 and 8. So it'll be about the same length as the other ones. It's not going to be longer. So we'll plan for it to take 1 hour and 15 minutes about. Build in some extra time if you need a little bit, and then some time to upload. So I'll kind of plan that things will start to be wrapped up by 3:30. And I put some review materials, practice problems up in Canvas as well, if you want to check those out. But otherwise, we've got exam on Monday, and the last homework assignment is due on Thursday of this week. So any questions about the rest of the semester? It's very sad. Our time is coming to an end. Okay, so then we'll get going with the plan for today. So last time we were talking about type 1 and type 2 errors and connecting this back to the significance level. And so just to recall these ideas, just to put some scratch work over here, type 1, this is what we called a false positive. Okay, so positive meaning the test is significant. So you falsely determine that the test is significant. And so another way of saying that is you reject. What you would do if the test was significant is you reject the null hypothesis when what's important here is that this is an error. So that you incorrectly reject the null hypothesis when it is actually true, when you shouldn't have. And type 2 error, same idea, except that's a false negative. So that would be the situation when you determine that the test is not significant when it is. So in other words, this is when you say that your test is not significant when the result should have been significant. So you incorrectly fail to reject HO when HO is not true. And then we can kind of reframe what the significance level is in terms of these errors. So the significance level that we denote alpha is equal to the maximum amount so it's the maximum amount of the type 1 error that your the tester is willing to accept. So we generally set this, usually the default is at 5%. We're willing to accept that 5% of the time we're going to get a false positive. So kind of the equivalent here that you might want to think about is if you're thinking about yourself as being a juror in a trial, this 5% is like the maximum amount of doubt that you're willing to accept before you're able to convict someone. So this is like the reasonable doubt. And so today I want to kind of talk about how we can calculate how likely we are to make a correct conclusion. So we'll look at the positive side of this today. So last time we calculated what are the odds of making errors. Any questions about those definitions so far? Okay, so here's the case study we'll take a look at first. So let's say there's like some cosmetic company and they claim that 3% of people that use their lotion have some allergic reaction. Let's just say, you know, you're the, you know, the mob rule on social media. So we all have megaphones now. So, you know, you're suspicious that this company is lying based on some, let's say, like anecdotal data that you have from people that you know. But let's say you pick like a random sample of 50 people and you find that 3 out of those 50 people got a rash. So that's like, you know, 6% of your sample. So you think that this company is lying or you're suspicious that they might be lying. So let's set up hypotheses for this test in terms of notation. So I'd like you guys, I have a poll here, I'll open. In other words, you're telling the truth. So 3% of all people have an allergic reaction. So in other words, we're saying P is the proportion of all people that would get an allergic reaction. So that's going to be 0.03. The reason why we wouldn't use P hat is because whenever we're stating hypotheses, we should be using population parameters, not referring to statistics from a sample, which is what P hat does. And then for the alternative, for the same reason as the previous one, we wouldn't use the P hat as a hypothesis. So we're never going to use P hat or X bar when we state our hypotheses, but we should be using the population parameter. And in this case, it is not a two-tailed test. It's a right-tailed test because this person is suspicious that P is bigger than that, right? So they want to prove that it's more than 3% of the population. Any questions about that? Good, I think most people got that. So next up is, let's think about these errors. So just one question here with 2 options. which of these is correctly stating what a type 1 error would be in this context, right? So remember, with a type 1 error, it's a false positive. So this means we reject the null hypothesis, even though the null hypothesis is true. So we just need to state that in the context of this problem. So rejecting the null hypothesis here would mean we are therefore saying that they're lying, right? And so the type 2 error here would be a false negative when we claim the test is not significant when it is. It should have been. So you conclude that the company was giving accurate statistics when in, or parameter here, when in fact they were lying, right? More than 3% were getting a reaction. So definitely be sure that you're kind of practicing and explaining what these different types of errors are in these different contexts. Any questions? Okay. So then if we want to calculate the probability of making a type 1 error, right? So the way that we can write this out using a conditional probability would be, okay, so the null hypothesis is true, however, we incorrectly rejected it. So let's calculate the probability of that. And something that's important to make note of back here is, okay, that's your kind of benchmark for rejecting. Is you say, okay, I'm going to pick a random sample of 50 people. If 3 out of those 50 people, 6% of my sample, has a reaction, then that's going to be my point for saying this company lied. So kind of that part up top was kind of saying, here's what we're going to do. That's our kind of decision for rejecting. This stuff over here, HO is true, means we assume this, that P is 0.03. So we've got one thing, which is what's the claim, and the other thing is when are we going to reject that claim. So if we let X denote the number of people in our sample of 50 that get a reaction, what is the distribution for X? How can we describe that probability distribution?
Would it be binomial?
Yep, thank you. That's right. So this would be binomial. And our n value, right, we have a sample of 50. And now we assume from the null hypothesis, this is where that null hypothesis comes in, that P is equal to 0.03. So what we want to calculate is what is the probability that X, when are we going to reject if it's more than 3 out of 50? So that would be X is bigger than 3. Okay, notice we're not including 3 in this, right? Because it says more than 3 people. And so for this is where we can use R, right? So here we can say 1 minus P binom, N is 50, P is 0.03. So the question is, what would we put in here? The question is, so first thing is the type 1 error, right? This is going to be the probability that we reject the null hypothesis when the null hypothesis is true. So to calculate that, we assume the null hypothesis is true, and we calculate what is the probability that we're going to reject. And based on what we're told here, rejection means more than 3. So we want to calculate the probability that X is strictly bigger than 3, given that X is being picked out of this binomial distribution. So someone chatted in 4 as what might go here. But keep in mind, we're trying to calculate the probability that X is equal to 4, 5, 6, 7, all the way up to 50. If I put in 1 minus P binom 4, P binom 4 would look like that, right? It includes 4. So this is saying what is 1 minus the probability that X is less than or equal to 4. And so this would tell me the probability if X is 5, 6, 7, so on. So if I include the 4 over here, right, that means it's going to exclude this because we're calculating the complement. So we don't want a 4 there. How could we fix that?
Would it just be the 3 then? 3.
That's right. So here, we're just going to put a 3 over here. And these things are tricky. So I would say don't rush through that step. Put some thought into what is the cutoff. And that depends on, right, whether we have an inclusive or exclusive thing over here. But we want to calculate the probability that at least it's clear that we're going to reject this if X is more than 3. So we want to calculate the probability that X is equal to 4, 5, 6, 7, 8, 9, 10. So I want to include the 4 in that. So here we would have our formula that we can enter into R, calculate that, and this comes out to, you can check this, 0.0627. So this is saying we have about a 6% chance at this rate, if that's our cutoff, we have a 6% chance of incorrectly claiming that the null hypothesis is wrong. So we have a 6% chance of accepting the alternative hypothesis and making a mistake when the null hypothesis was wrong. So what might happen here if you make a type 1 error? What might be the ramifications of that mistake?
So would it be the same as in part B? You're saying that more than 3% of people have a reaction, but the company is telling the truth?
Yeah, so what might happen then if you make that mistake? So you go ahead and say, okay, I found 4 people out of 50 that that did this, but you were incorrect. And so then you go online and you say this company's lying, they're giving people rashes. What might happen?
You get sued for
Yeah,
slandering.
probably you're going to get sued. Yes, you're free to say whatever you like. However, if it is lying and that is attacking someone else's character or incorrectly attacking a company, yeah, then you might be open for libel. Maybe not, depends on how vociferous you are online. Yeah, and so here, and then you can think about, well, what would the ramifications of type 2 be? Well, now there just might be a lot of people that are getting reactions from this lotion. Any questions about that? So if we were to perform this hypothesis test at a 5% significance level, and we actually did observe, say, that X was equal to 4, right, then the p-value is equal to the probability that X is bigger than or equal to 4, given that HO is true, right? So when we calculate the p-value, this is saying what is the probability of getting a sample as or more extreme than the observed. So that is, by definition, what the p-value measures. So again, if we assume that HO is true, it's the same assumption that we had up top. And in fact, right, it would be the same exact probability that we have up top. So the 50 and the 0.3 come from the sample size and the claim in the null hypothesis. The 3 comes from the fact that we want to exclude 1, 2, and 3, and just want to consider what happens if we had things like 4, 5, 6, and so on. So here's our p-value. We're going to compare this to significance level, which let's say we choose a 5% significance level. If I have a p-value of 0.0627, just kind of want to check in and ask you guys, well, what would the conclusion of this test be? I don't know if there's some part of my answer seems to be chopped off. But I think you guys are figuring it out. Okay, take another 10 seconds, please. If you haven't gotten your answer in. Thank you. So we're split here. At least we're split between the two possibilities. So the one in the middle, which is, let me share the results here. The one in the middle, which says reject the alternative hypothesis and accept the null hypothesis, that's right. That's never going to be the result of a hypothesis test. So you're either going to reject the null or not. And in this case, since our p-value is greater than alpha. Remember, larger p-value means less significant, means that the sample is becoming more and more likely. It's falling more in line with the claim in the null hypothesis. So when the p-value is bigger than alpha, that means we've gone beyond the maximum amount of type 1 error that we're willing to accept, right? We're willing to accept 5% significance level. We already calculated this exceeds that error, so this would mean we reject the null hypothesis. Or excuse me, this would mean we fail to reject the null hypothesis. Okay, so they don't say that the company is telling the truth. They just say, we don't have evidence to say that this company is not telling the truth. So there's a difference in saying that. Yeah, I'll just stop there. Okay, so again, just to connect this back to these notions of type 1 error and significance level, our type 1 error was 6% if we're making our decision based on what was highlighted in pink. So if that's what we're going to do, we're choosing a 5% significance level. If we get a sample that has 4, okay, we've exceeded that type 1 error. So here, if x equals 4, this wouldn't work. However, if we take a look at what happens we can think, well, what if we had a more extreme example like x equals 5? 5 out of the 50 people had a reaction. Right, we would do the same sort of thing that we had up in part D, except now we increase that to 4. in which case, if X was equal to 5, this would be less than the 5% significance level. So here we would reject HO. And then you can see we would, if it were even more extreme, if X were 6, 7, 8, 9, 10, etc., those would be even more and more extreme. So this kind of tells us how extreme, what does our test statistic need to be in order for us to reject the null hypothesis. So these sets of values are what are called the rejection region. So these are the values of the test statistic for which we would reject the null hypothesis. And again, we saw that X equals 4 was just not quite extreme enough. We needed to go out one more value in order to get extreme enough. Any questions about that, this example, this question, first question? So it kind of connects in all these ideas, p-values, errors, significance levels. These are all connected ideas, as we've seen. Okay, so here we formally define what the rejection region is in general. This is also called the critical region. And just like we said before, it's going to be the set of values of the test statistic that we reject HO. And we'll see when we have a two-tailed test, we're going to have two rejection regions, or the rejection region is going to be a union of two sets. When we have one-tailed test, it's just going to be one set. So in the previous example, again, we had a rejection region of 5, 6, 7, all the way up to 50. So we would say this is our rejection region or our critical region, and the critical value in this case would be 5. I should kind of make note that we're saying critical values when X is equal to 5. So here our test statistic is how many people out of 50 had a reaction. So this gives us another way of making a conclusion from a test without actually having the p-value, right? We can just say, what was my test statistic? Is my test statistic in the rejection region? Okay, any questions about that, those terms? Yeah, so definitely, be prepared on the exam or multiple choice to, identify rejection region, critical values, that sort of stuff. Was there a question someplace, or is that that was a no question? Okay.
There's a thumbs up for no question.
Okay, thanks. Okay. So, okay, then in question 2, we kind of looked at this one last time, although we didn't actually have die that we could play with, but we kind of thought about the context where we have a die, instead of having a 6-sided die, we have a 10-sided die with numbers 0 to 9 on it. And we want to figure out whether the die is fair or not. So notice it's a two-tailed test. We're not claiming any direction of the bias. So we're gonna, if the die were fair, right, 50% of the rolls would land on an even number. So P is the proportion of rolls that land on an even number. And if the die is not fair, then this wouldn't be 50%. So in this case, we're calculating the p-value. So it's going to be the probability of getting a sample as or more extreme if the null hypothesis were true. Right? Since it's a two-tailed test, we're going to be calculating the area in a tail and then doubling it. And here we're rolling it 20 times. So if we rolled it 20 times and the coin was fair, right, we would expect to get 10 of them to be even. I said coin, but it's a die here. So we're assuming the die is fair. We would expect 10 of them to land on an even number. We found 7. So more extreme, as or more extreme than 7, does that mean greater than or equal to 7? Or are we going to consider something less than or equal to 7 to be more extreme? So any thoughts on that?
We want less than or equal to, right?
Yeah, thanks, David. Yeah, so we're going to want to go less than or equal to because, right, our observation of 7 is below what we would expect. So we would think of things that are even more extreme as things that are like even more bizarre, right? 7 out of 20 is not a lot. We would consider 6, 5, 4, 3, 2, 1, those to be more extreme, further away from the null hypothesis. So here, if X is equal to the number of even rolls out of 20, then if HO is true, right, we assume that P is equal to 1/2. So we could calculate it with that formula in R. P binom 7, 20, 0.5, and then double it because it's two-tail. And so this comes out to about 0.263. So that would be our p-value based on that sample. That's pretty big. Probably not going to reject that based on any, I mean, I've never seen a significance level bigger than like 10%. Okay, so in this case, we can see that okay, I don't think oh, I see. Just to kind of look ahead to the next one, if we were to use a 10% significance level, which again is about as big as it gets, even at that kind of pretty small benchmark, we wouldn't meet it. Our p-value is bigger than that. We would not reject HO. So X equals 7 is not in the rejection region. So that's one way we could make a decision is by looking at the p-value. And then another way, we'll take a look down here, is to find the rejection region and then look at whether our test statistic is in the rejection region. not kind of drawing the full binomial distribution, but the idea here in this case is, right, we would have 10 in the middle. That would be the expected value if we are rolling this 20 times. And so if we're using a 10% significance level and we're doing a two-tailed test, this means we're going to have kind of two critical values. I'm just going to denote them XC1 and XC2. And, you know, maybe there's more bins out over here. They get smaller and smaller. We're going to find values so that how much area should be in this tail, for example.
5%.
Yeah, so if we're using a significance level of 10%, that means if I had a value over here that had exactly 5% of the area above it, that would be enough, right? Because that would give me, therefore, a p-value of exactly 10%, which just makes that benchmark. So in other words, we need to find values that give us an area, and what's important to note here is that this is a two-tailed test, so that's why we split it up into two. For a one-tailed test, this process is a little bit different. But we'd like to find these values. So XC1, if I'm doing this in R, this is where that Q binom comes in handy. So this is the quantile binom function. So I'm going to enter the quantile that I'm interested in, which is the area over here. And then N is 20, P is 50%. So this is giving me 6. But we need to be careful here because this is a discrete distribution. So let me just check what the p-value would be if I used 6. So it would be, because it's two-tailed, right, it would be 2 times p binom 6, 20, 0.5. So I'm going to see if 6 gets the job done. That it actually is a little bit too big. Okay, and again, the reason why this doesn't give me exactly 10% is because this isn't continuous. So there's not a perfect cutoff. So this Q binom gave me the closest integer to it, but that's not enough. So we actually need to bump it down a little bit less. So x equals 6 is not in the rejection region. Okay, but 5 works, and you can check that calculation with 5 would give us a p-value that is less than 10%, whereas 6 is not quite enough. And then we can do the same analysis to find XC2. Okay, we have the same value for N, we have the same value for P, but now we would want to say this value should have how much area to the left of it. That's how Q binom works. So if I have 5% of the area above XC2, then we should have 95% below. But hopefully you see where I'm getting these numbers from, because it's going to change based on what the significance level is and based on whether we have a one or a two-tailed test. So any questions on where we got the values in this formula from? And so if you're doing this in R, it tells you 14, but again, it's rounding things, so the 14 isn't going to be quite extreme enough. So you need to bump this out and go one step further to get beyond that threshold of 10%. So if you use 14, you'll have the same issue. Your p-value will be just a little bit too big. So our rejection region here would be the union of these two sets. So it would be all of this stuff in the right tail, 5 all the way down to 0, and then everything above 15 and above. So it'd be 15, 16, 17, 18, 19, and 20. So this just gives us another consistent way of making decisions. I didn't need to do anything in part C. I could have just gone straight to part B, found the rejection region, and then looked at my value and said x equals 7. Oop, that doesn't fall in the rejection region, so I fail to reject, and we would get the same outcome. And in this case, for a two-tailed test, we have two critical values. The critical values are the endpoints. So that would be the 5 and the 15. Okay, so I'll just say when you're kind of out in practice and maybe reading statistical work that somebody else has done, just some people live in the world of p-values, some live in the world of rejection regions. But in any case, they'll give us the same result. Okay, so the very last thing I want to talk about this semester, so kind of fight back the tears while we're trying to work on this last idea here, but that would be the power of the test. So just to kind of look ahead to what we mean by that, we'll calculate it in this example. So this is the probability of being correctly rejecting the null hypothesis. And so usually this is the thing that you're interested in. You would like to maximize the power of the test, right? So this is sometimes where you might choose the significance level based on how I want to maximize the power of the test, how I want to maximize the probability of being correct. So let's see how that kind of connects into these ideas of type 1, type 2 errors, and so on. So here, let's say the experiment that we're doing is we're working with a species of snake, and we're trying to come up with the mean length of the snake. And so we're told that the population of these are normally distributed. We don't know what the mean is. The standard deviation of the population we do know is 4 centimeters. And there's a claim that the population mean is 25 centimeters, and you believe that is bigger than 25 centimeters. You go out and collect a sample of 30 snakes, and you're going to use a significance level of 5%. So one distinction between this one and the previous examples is here we have a mean. The previous examples, they were dealing with proportion. So the null hypothesis here would be that the mean length of all of the snakes of this species is 25 centimeters. So we would state that using population parameter. In this case, for mean, we use mu. So we've got here a one-tailed test, which is also another difference from the previous one. So in these cases with means, right, we approximate the null distribution using the central limit theorem. And in this case, we know what sigma is. And so when that happens, we use a normal distribution. Okay, just recall, if we didn't know what sigma was, then we would use a t-distribution, right? And we would use standard deviation in the place. So using the central limit theorem, what would the center of this distribution be?
$25.
Yeah, so we assume the null hypothesis is true. So if the population mean is 25, then we would expect most of our sample means, right, to be 25. This is just saying the center of the sampling distribution for the mean is equal to the population mean. And then via central limit theorem, we know that the standard error, right, is not going to be the standard deviation, but we would take that and divide it by the sample size, which is 30 snakes, the square root of the sample size. So when we're doing a mean, right, we're not using the binomial distribution, but we're using either a normal or a t-distribution for and the central limit theorem. So the picture for what we're trying to find right, here's our distribution for X bar. We're going to find this critical value where the area in the right is equal to the significance level. And now we just have a one-tailed test, so we're going to put all of that in the right tail. Okay, so the reason why we're only looking at the right tail is because of that alternative hypothesis. So here we can use the Q-norm function again, right? Similar to the way we used Q binom before. So in here, right, goes the area to the left of XC. So in this case, that's going to be 95%, 0.95, because we have 5% to the right. So here we go, right? We've got our mean standard error. And this comes out to, let me double check that, I think 26.2. So this tells me exactly what this value is. And this is continuous distribution now, so I don't need to worry about if they rounded off and got anything, right? This is telling me that, no, 26.2, that's the value that gives me 95% area to the left, thus 5% to the right. So here, the rejection region is going to be continuous now. So it's a continuous interval of values, as opposed to with the proportion, we had a discrete set of values for X. I'm using interval notation. Another way of saying that would be if your sample mean is bigger than 26.2 or equal to that. And we would say the critical value here, which is just 1, is 26.2. Then you could look at your sample. What was my mean? Was my sample mean in the critical region? If so, I'm going to reject. If not, I fail to reject. Okay, so then let's now take a look at the type 2 error. So the type 1 error connects to this notion of the significance level. The type 2 error is going to connect to this notion of power of a test. So remember, type 2 error is false negative. We don't reject it when we should have. Right, so that's when we should have rejected it, but we failed to. So another way of saying that is we don't reject, I left out an important part here. We don't reject the null hypothesis when the alternative is true. Now we've got what it means for HA to be true, which is that the mean is actually 27, and up top, we calculated at least what it means to reject something. So that's going to connect back to what it's going to mean to not reject something. So we can use this rejection region that we found in the previous part. Okay, so we're going to make this correction over here that we are actually, the sampling distribution for the mean is not centered at 25, but it's centered at 27. So we've got a delay here. There we go. But the standard error is the same, right? We still have the same population standard error, and we still have the same sample size. And here, don't reject means X bar is strictly less than 26.2. All right, so all that green stuff is kind of connecting to each other. We figured out what it is to reject, so not rejecting would be the opposite. So we're trying to calculate what is the probability of getting a sample mean, because we want to calculate the probability that we don't reject X bar is strictly less than 26.2, given the alternative is true, that the mean is actually bigger than that. We're told the mean is 27. So this we can calculate by doing P binom 26.2, 27, and then 4 over the square root of 30. And with these continuous distributions, we don't need to get so concerned about are we including or excluding the endpoints, right? We do, as we saw with the discrete distributions. So this would tell us here we would have a 13.7% chance of making a type 2 error. And we denote the type 2 error with the Greek letter beta. Okay, type 1 is like alpha, and type 2 like beta. So just kind of going back over how we did these type 2 error calculations, and now we're just going to kind of attach to that we denote that with a beta. In part D, I want to calculate the probability correctly rejecting HO, given that HA is true. And this is what we want, right? Ideally, this would be like 100%. This is what we want to do. We're hoping to reject HO, and we're hoping that we do it correctly. And so comparing this to the previous calculation, right? In both of these cases, we're assuming HA is true. So I already calculated the converse of this, right? Or the complement of this, I should say. I calculated how likely it is that we don't reject it. So if HA is true, either we don't reject it or we do reject it. So I calculated this probability, so we can determine this probability using the complement rule. So to calculate how likely we are to correctly claim significance, it's 1 minus the type 2 error. So we can see in this test, right, we have an 86% chance of rejecting the null hypothesis correctly. And we call this the power. Yeah, but keep in mind, like,
Thank you.
Yeah, the alternative may or may not be true. So this is only considering the branch if HA is true. What percentage of the time are we going to correctly identify that? Perfect, right on time. The last page just has a couple of additional problems that deal with power. Just if you want to get some extra practice with this, these are, I think they're from the textbook more or less. I'll put up solutions to these if you want to check your work. And this, if you want to talk about these next time, I'm happy to do it. The power of the test, you're not going to see, I'm not going to make like 80% of the exam on the thing that we did on the very last day. So don't get, too consumed by this. Make sure you're practicing your homework and getting all that stuff done. You will see some questions about error types and rejection regions and power, but that's not going to be a huge emphasis on the exam. Okay, so I will stop here for the day. Thanks everybody for a nice class. And if you do have any questions, welcome to hang around afterwards. Otherwise, got office hours tomorrow. Welcome to stop by. And otherwise, I'll see you on Wednesday. We can just kind of chat about the exam or the homework, whatever. It'll be mostly like an office hour type of thing. Okay, well, have a nice afternoon, everyone, and I'll see you guys on Wednesday.